Hello friends, in previous lecture we have talked about the dense subset, no-head dense subsets of metric space. A subset A of metric space XD is said to be dense if its closure is whole set. Means all points in that A or every point in metric space X is near to some point of A. Very near to some point of A. Means every open sphere about X must contain at least one point of A. And that's why A closure is equal to X. On other side, a subset A of metric space XD is nowhere dense if A closure interior is equal to empty set. A closure interior is equal to empty set. Means A closure doesn't contain any open set. A closure must not contain any open set. Every point must not be interior point. Every point in a closure is not interior point. Okay. So we'll take the equivalent conditions or simple observations for that. If XD is a metric space and A is subset of X, then following statements are equivalent. A is dense in X, the only closed superset of A is X. Third one, the only open set disjoint from A is phi. A intersects every non-empty open set and A intersects every open sphere. So we'll prove one by one. Okay. So proof 1 implies 2. Suppose A is dense in X. Suppose A is dense in X. What this implies is, therefore, A closure is equal to X. We know that A closure is the smallest subset of X, smallest closed subset of X containing A. Now, since A closure is smallest closed subset of X containing A implies the only closed superset of A. This is say A and this is B. From A and B, A closure is equal to X. Is only superset A closure is equal to X is only closed superset of A. There is no any closed subset in A closure and X. A closure is the smallest closed subset, but A closure itself is X. So X A closure which is equal to X is only one closed superset of A, and therefore 2 hold. Okay, thus 1 implies 2. On same line, we'll prove one by one. Now 2 implies 3. Implies 3. Suppose the only closed superset of A, the only closed superset of A, superset of A is X, then claim only open set disjoint from A is phi. Okay. Only open set disjoint from A is phi. Claim only open set disjoint from A is phi. If you assume that let G be some open set disjoint from, let G be open subset of X disjoint from A, and G not equal to phi. Then for X belongs to G, there exists some R greater than 0 such that SRX is contained in G. In this case, SRX intersection A must be phi, as G intersection A is equal to phi, as G intersection A is phi and SRX is contained in G, and therefore X doesn't belongs to A closure. X doesn't belongs to A closure, is it right? And therefore A closure must not be equal to X. Contradiction to hypothesis. Only closed superset of A is X, that is A closure is equal to X. Okay. This is contradiction to hypothesis. Okay. Therefore, our assumption is wrong. A intersect 3 implies 4. A intersect every open set. A intersects, claim A intersect every open set. If A doesn't intersect some open set, if on contrary, if A intersect every open set, okay, on contrary, if A intersect doesn't intersect, what is our aim? A intersect every open set. A doesn't intersect any open set. Any open set. Or what we are assuming, the only open set disjoint from A is phi. Okay. The only open set disjoint from, since only open set disjoint from A is phi implies G intersection A is not equal to phi for any open set G in X, G not equal to phi. Then for open sphere also, every open set is open sphere. Okay. 4 implies 5 as every open sphere is open set. Okay, and therefore result hold. Then 5 implies 1. Suppose A intersect every open sphere. For any x belongs to X, SRX intersection A is not equal to phi for every r greater than 0. And therefore X belongs to A closure for every x belongs to X, and therefore A closure must be equal to X, and therefore A is dense. A is dense. So what results we proved for dense sets on same line results holds for novel dense. Result holds for novel dense sets. So what is the corresponding result? If XD is a metric space and A is subset of X, then following statements are equivalent. A is nowhere dense in X, then A closure doesn't contain any non-empty open set. A closure doesn't contain any non-empty closed set. If A closure contain non-empty open set, then every point in that open set is interior point of that open set, which is also interior point of A closure. And we are getting A closure interior, which is phi. For that we will get contradiction. Okay. A closure doesn't contain any non-empty open set means A closure must intersect every open set. Is it right? Non-empty open set means every non-empty open set has open subset disjoint from A closure. And that again, that is the for open sphere. Okay, that result holds. So on parallel line we can prove these results. Okay, so this is exercise for you. Now we'll take the next theorem that A is novel dense in X if and only if X minus A closure is dense in X. What is the theorem? Let XD be metric space. Let XD be metric space. Then subset A of X is nowhere dense in X. If and only if X minus A closure is dense in X. So we know for subset A of X, for subset A of X, A interior is equal to X minus A closure. Okay, that is X minus A complement is closure. This is the known result to we have. Now replacing A by A closure here. Replacing A by A closure in 1, we get A closure interior is equal to X minus A closure, its closure. Oh, sorry. A closure interior. So X minus this one. Is it clear? So we will get this step. Replacing A by A closure. Sorry. X minus A, its closure here. We'll get this. Okay. A closure interior. So from this, what is now? Now A is no held dense in X if and only if. Now A is no held dense in X if and only if A closure interior is equal to phi. If and only X minus A closure, its closure is equal to phi from 2. Right? If and only X minus A closure equal to phi, means what will be this set? Therefore, X minus A closure, whole closure must be equal to X. Must be equal to X. If and only if X minus A closure is dense in X. Is dense in X. Is it clear? So only we are using this result from result relation between interior closure etc. which are derived after properties of interior and closure of the set. That result we are using here. Okay. Then one more result is that finite union of no held dense sets in metric space XD is no held dense. Next theorem. Finite union of no-Weyl dense subsets of X. No-Weyl dense subsets of X is no-Weyl dense subset. No-Weyl dense subset of X. So proof. Let A1 and A2 be no-Weyl dense subset, be no-Weyl dense subsets of X. Implies A1 closure interior is equal to phi, which is equal to A2 closure interior. Claim A1 union A2 closure interior equal to phi. interior is equal to phi. Now A1 and A2 are no Haldane since A1, A2 are no Haldane. Implies A1 closure, A2 closure doesn't contain any open sphere. Doesn't contain any open sphere or any open set. Now A1 closure union A2 closure. Moreover, A1 union A2 closure is equal to A1 closure union A2 closure. This implies A1 union A2 closure is equal to A1 closure union A2 closure can't contain any open sphere. Contain any open sphere. Okay. And therefore, A1 union A2 closure interior must be phi. Okay. Therefore, A1 union A2 is nowhere dense. So, by using induction, we can say that finite union of nowhere dense subsets of X is nowhere dense subset of X. But countable union of nowhere dense subsets of X need not be nowhere dense. So, note countable union of nowhere dense subsets of X need not be nowhere dense. Justification in RU singleton X is nowhere dense set. Nowhere dense set for any X belongs to R. Because it doesn't contain any open set, open sphere, because open sphere is always the open interval X minus R to X plus R form. Therefore, now union of singleton X belongs to Q is equal to Q is such that Q closure interior is equal to R interior is equal to R in RU. Okay. Implies Q is not nowhere dense. In RU. Thus, countable union of we know that Q is countable set. Okay. Thus, countable union of nowhere dense sets need not be countable. Need not be nowhere dense. Is it clear? So, with the discussion, today we'll stop our session here, and also I like to conclude this completely chapter here. So, for novel Dane subsets, geometrical visualization of that subsets is very important. And what metric is defined on that metric space also plays very important role. In discrete metric space, XD, empty set is only nowhere dense, while whole metric space is only dense set in itself. If I take any proper subset other than empty set, then it is open as well as closed. So its closure is itself and its interior is again itself. And that's why empty set is only unique set which is nowhere dense in discrete metric space, while whole metric space is unique subset of discrete metric space X which is dense in it. Okay, and that's why discrete metric space is a different metric space. What is happening in with respect to usual distance function that doesn't happen with discrete metric. Keep this in mind. Okay, thanks for listening lecture carefully. Bye bye.